Welcome to the length of a curve. In this lesson we're going to learn how to find the length of a function, and when I say length of a function I mean pretend that this is a piece of string and we're following along it. So how long is that piece of the function? And I know already that y tells me the location on my function, y prime tells me the slope of my function, y double prime tells me the concavity of my function, and if I take the integral of my function I find the area underneath it. But none of those really help me figure out the actual length of my function, so I need to do that a different way. One of the easiest ways to find the length of a function is to break our function into smaller pieces, because if it's continuous it'll be locally linear, which means it looks like a line at each small piece of it. And we know how to find the length of a line because we can use right triangles. So I'm going to pretend that my this hypotenuse of this triangle is approximating the length of that function. And if I want to approximate it better, I can make smaller triangles, but I made mine kind of big so you can see what's going on. So really I need to figure out how long is this line, because that's going to approximate how long my function is. And in order to do that, we can use right triangles like this one over here. And I know this side is delta x because that's the change in x, and the height of my triangle is delta y because that's my change in y. So the formula, based on Pythagorean formula, delta x squared plus delta y squared, and if I take the square root of that, that's equal to the length of my hypotenuse. And now I've got all of these little triangles, so if I add up this hypotenuse plus all of the other ones that I get from my other triangles, that will tell me the length of the curve. And I know that if I'm adding a lot of things, that I'm using an integral, which we're going to see on the next slide. We need to rearrange this to make it look more like an integral. We're looking to have a dx here, so we need to factor dx out of each one of these. And dx and delta x are pretty similar as long as your change in x is very small. So I can factor out a delta x, delta x squared from underneath the square root, which turns into delta x when we take it out of the square root. And really, this is the derivation of how we get our formula, but that's not so important to know. The important thing to know for the AP exam is this formula right here. So it goes from a to b. Those are our interval. That's the interval that they give us. The square root, 1 plus, and then the important part for us to really know, this is where we plug in our derivative of our function. Here's an example of a type of question where you might have to find the length. They'll say something like determine the arc length or determine the length of the curve of the function. And for this example, it just says determine the length of y equals the square root of x plus 2 on the interval 1 to 7. So those are our x's. First thing we need to do is find the derivative of y. So dy dx is 1/2 x plus 2 to the negative 1/2, and we would use chain rule, so that's technically multiplied by 1, but we don't have to put that. And now we have to fill in our integral. So we write our integral from 1 to 7 because that's the interval that they gave us. The square root and the 1 plus are always in the formula, so the only part that we're really filling in is this right here where we're putting dy dx into the integral. So 1 plus dy dx squared dx. And for this one, I used a calculator to evaluate it to get 6.268. So now here's an example for you to try. Find the length of y equals x squared on the interval 1 to 4. So pause the video here, take a few minutes, try this problem, and then when you restart the video, we'll look at what the answer to this is. Alright, first we have to find the derivative, dy dx equals 2x, and then we do our integral on the interval that they gave us from 1 to 4. The square root and the 1 plus all stay, so the only part that we're plugging in is the derivative that we just found. And when we take the integral of that, and again I used the calculator for this one, which you don't necessarily have to, you could do U substitution, but the answer should work out to be 15.339, and make sure you go to 3 decimal places. Now, we don't always have rectangular coordinates, so sometimes we have parametric, and the formula is really similar because it's based on the Pythagorean theorem. So we're going to start from the same place that we had before. Delta x squared plus delta y squared. Take the square root, gives you the hypotenuse. This time, instead of trying to get to dx, we're trying to get to dt, so we need to factor out a delta t squared from each of those, which gives us this extra delta t over here. And we end up with the important piece of all of this, the equation down here. This is what you need to know for the AP exam. The arc length of a parametric curve goes from A to B, that's our interval. Square root, this one looks a lot more like the Pythagorean theorem, so all we have to remember is that we're plugging in dx dt squared plus dy dt squared and taking the square root, so it's very similar to the Pythagorean theorem. And again, just like rectangular problems can ask you all sorts of different ways to find the length of the curve. They might say find the length of the curve, find the length of the function. This example says find the length of the curve defined by x equals 3 sine t, y equals 3 cosine of t on the interval 0 to 2 pi. They tell us this time that our variable is t, but they don't always have to tell you that, and it's kind of implied because this is a parametric equation that the interval will be for t. So the first thing we have to do is find dx dt, which is equal to 3 cosine of t, and then we find dy dt, which is negative 3 sine of t, and then we take both of those and plug them into our interval format that we've memorized from the last slide. Our interval goes from 0 to 2 pi because they told us. We have the square root because that's part of the formula. So we plug in dx dt here, and that's squared, and then dy dt here, squared. You could do this with a calculator, or this one you can do by hand pretty easily, because when you distribute that squared, you get 9 cosine squared t plus 9 sine squared t, and then you factor out the 9, but I know that cosine squared t plus sine squared t is just 1, which makes it a lot easier to evaluate, which is 3, so when I take the integral of 3, I get 3t from 0 to 2 pi. So plug in my 2 pi, plug in 0, which gives me, that's my answer. You could also do this with a calculator and get 18-ish, whatever, for your answer. If this is a no calculator part, obviously, they'll be looking for 6 pi as the answer. So here's one for you to try. Determine the length of the curve given by x equals t squared minus 2t, y equals t plus 1 on the interval from 1 to 2. And they didn't tell you that that was the interval for t, but it's kind of implied because these are parametric equations with the parameter being t. So pause the video now, take a couple minutes to try this problem, and when you're ready to check your answer, restart. Welcome back. So the first we take the derivatives. Dx dt is 2t minus 2, and dy dt is 1, and then we take each one of those and plug them into our general format. So we have our interval goes from 1 to 2, the square root is part of the formula, and then we plug in dx here, squared, and then dy there, squared. I evaluated this one with a calculator, but you could also do this by hand. So 1.479 is our answer. And that is it for lengths of a curve. If you have any questions, feel free to ask. If you are watching this at home, write down your questions so that you can ask me the next time you see me in class.